Welcome to breadboarding. This is video 38 in the Breadboard PC series, and in this video I'm going to be continuing the DMA diagnostics that we started in the previous video. So this is part of the overall project to develop a IBM PC compatible computer on solderless breadboards, and later in the series going to be looking at seeing if we can run an early version of Windows. Now, in the last number of videos we've been trying to boot and run DOS from floppy disk. We've managed to get early versions of DOS, so PC DOS 2.10, MS-DOS 2.11, managed to get those working, but later versions of DOS we've been unable to get working for one reason or another, mainly due to floppy disk controller, DMA controller type issues. So in the previous video, for which there will be a link at the top if you want to go back and have a look at that, or there will be links in the description below. So one of the suggestions from one of the viewers was to try Ruud Diagnostic ROM. So in the previous video I covered converting Ruud Diagnostic ROM, which is available on minerzero-degrees.net, and this basically replaces the BIOS and monitor ROM and does diagnostic testing. It works with our monochrome display adapter video card. We ran this test, showed there were some problems with the DMA controller. What I have done is updated that from version 6, which I produced in the previous video, to version 7 and version 8, and I'll just show quickly what those look like. So here's the diagnostic output. You can see here this is version 8, and all I've done with these later versions is I've taken out some of the memory tests because that was taking quite a long time, and I've also changed so that the DMA tests are no longer critical failures, so it'll actually carry on after a DMA controller failure, because they're not dependent on the DMA controller for doing the memory refreshing, so it's quite safe to continue if there's a problem. So you can see that's the first pass there, and the ROM failures at the top there just because we don't have any ROM actually in the memory map there, so that's expected. Now what I have done is run this over an hour or more, and depending on the current conditions the number of DMA controller failures could be between 1 in 10 and 1 in 3, and it looks like it is very much a timing issue, and I'll explain about what I've looked at to try and actually get to the bottom of it. So what we're going to do is to speed this up. We'll jump to the end of this series. Okay, so we've now completed 10 passes. And you can see there that there's 2 failures from the DMA controller in that time. And when I've been running these tests over an extended period of time, it does vary randomly, but generally it's between about 1 every 3 and about 1 every 10. So it's certainly erratic, and these tests here are very simple and straightforward, just writing to registers and reading them back. So it does indicate that something weird going on, which I've been trying to get to the bottom of over the last 3 weeks or so. So what I'd like to do now is just to show you quickly how complicated the process of reading 512 byte disk sector off of a floppy disk is, and what all the different processes which are at play on the original IBM PC. So this diagram basically shows, sort of in this sort of rather sort of zigzaggy way, but it's probably the easiest way I've found to represent what's going on here. So what happens to start with is the BIOS will do an interrupt 13, which is 19 decimal. And what this will do is to pass in what operation it wants to do, so a read operation, what the RAM memory address we want to load the sector to, the information about the location of the data on the disk, so the head, the cylinder or the track, the sector number and the number of sectors to transfer. And the BIOS will do various checks to do with internal disk parameter tables, whether or not the disk has been changed and needs to be reread, and see what the media are and things like that. And then what it will basically do is to send the DMA controller channel 2 the RAM address and the byte count of the number of bytes you want to actually read from the floppy disk controller. So in this particular case, if we were doing just one sector, 512 bytes, then in fact it would actually be 512 minus 1 is the count parameter passed in here. What it will then do as well is to set the DMA page register for channel 2 to be the required address. So This basically allows us to set the top 4 address bits on the address bus, so effectively we can choose which 64K segment we actually want the DMA controller to work on. One of the limitations of the original PC DMA controller, it could only do DMA within one 64K segment. The BIOS then sends the read command to the floppy disk controller, and basically at that point then the BIOS basically just sits around then and waits for the interrupt 13 to complete. So in fact the BIOS actually then goes and waits in a loop, waiting for interrupt 6 in a timer loop to complete. And the rest of this process actually goes on between the floppy disk controller and the DMA controller. So the floppy disk drive reads the data byte, the first data byte, then the floppy disk controller signals the DMA controller using DMA request 2 that it's got some data. The DMA controller requests the CPU bus via the HRQ DMA, and then it gets acknowledgement that it's got control of the bus via the hold A signal. And then the DMA controller will then actually set the top 8 address bits from the data bus from the DMA controller to a latch, which we'll look at on the next diagram, and this is using a signal called address strobe. So this basically sets the top 8 address bits of the bus here in the latch, and then the DMA controller signals the floppy disk controller using the DAC2 signal, say can you put the data on the bus. Now the DMA controller also puts the RAM address on the bus and sets IO read low and memory write low, and what this basically means is that when the floppy disk controller puts the data on the bus, then it will go direct to RAM. So the DMA controller does not directly see the data passes directly from the floppy disk controller to RAM. So the floppy disk controller then puts the byte that it's got on the data bus and it's written to RAM. The DMA controller returns the bus back to the CPU. It also increments the address until the byte counter is reached. So at this point in time, it will just sit there waiting for the next byte and the DMA request to come through, and it will go around this loop 512 times. Now, when it actually gets to the last byte, what it will then do is the DMA controller sets the end of process stroke terminal count. So EOP is inverted to become terminal count, and TC actually tells the floppy disk controller that the DMA controller has got all the data it needs. And then what happens is the floppy disk controller raises interrupt 6 to signal completion, and then the BIOS loop that's actually been waiting for interrupt 6 to complete will then actually complete, and the BIOS will then continue. Now the irony in all of this complexity is that if we were using programmed I/O to access the floppy disk controller, then in fact all that would be happening, rather than this loop here waiting for an interrupt, we'd actually just be waiting for polling the floppy disk drive to see if it's got a byte, write the byte to memory, and then wait again until such time as we got all the data you want. So really the DMA was a massive complication, and the irony is that from the 286 onwards that in fact programmed I/O was faster than the built-in DMA that was in the original PC. Later versions of PCI bus DMA I think were faster, but in this particular case the legacy DMA is slower on virtually every processor from the 286 upwards. So there's an awful lot of complication for not very much benefit. And in fact I think the Tandy 1000 and the PC Junior, which were two lower end computers at the time, they actually removed the DMA controller directly and actually used programmed I/O for the floppy disk controllers. So we've now have a look at the DMA design on the breadboard PC. So we've got our 8088 processor, which is a 16-bit processor internally, but it's only 8 bits on the outside world. So we've got an 8-bit data bus and we've got a 20-bit address bus. Now the limitation of the DMA controllers used in the original PC is they only had 16 address bus bits, so you could only ever work within one particular segment, and I'll explain how IBM worked around this in this diagram. We've got the various control signals, so the memory read, memory write that control the reading and writing to RAM, and the IO read and IO write that control all the peripherals. And then we've also got an interrupt line there. Now there was only one interrupt on the processor, but the programmable interrupt controllers allowed up to 15 interrupts to be handled on the design that we're dealing with. So then we've got the buffers and the latches between the microprocessor and the rest of the bus and the bus controller. Now the reason why this is important is that when the DMA controller is actually taking control of the system, then these latches will actually go 3 states, so they're disabled effectively, and the clock here actually has an input to it which is actually used by the DMA controller to suspend the microprocessor so that it can have, the DMA controller can have access to the bus. So we've got our address decoder, our read-only memory, so this is where the BIOS is. So in fact when we're reading the disk, then it's a routine and the BIOS is actually doing this. The RAM is where we're actually going to be loading the data to. Now the floppy disk controller exists actually as an I/O address, but it also has access to the data bus via the DMA controller. Now the bit over here is where we're going to be adding the DMA controller now. The simplest side of things is the DMA controller has a latch for the top A8 to A15 address lines, but it doesn't have anything to handle the A16 to A19s. This DMA page register is a very small memory. It's only like 4 bits by 4, and it's a rather unusual arrangement in that the DAC2 and DAC3 acknowledge signals are actually used to provide the 2-bit address for this. Now the tricky thing to understand here is that DAC2 and DAC3, when they're active, they're low, so there will never be a situation where we'll have 0 and 0 here. So the values on here are 1, 1, 1, 0 and 0, 1. So in fact the 0, 0 location that you might assume for the DAC0 is never actually used in this particular case. So this is the way how this 16-bit DMA controller is able to access the full 1 megabyte address range here. Now there is a limitation in that the DMA controller is only able to actually access data within this one page at any particular point in time. Now in addition to that, there's quite a bit of logic. The videos where I covered this, I explained this in quite a bit of detail. It's quite complicated. So there's various things to do with the weight and the DMA and the bus control. Basically there are some signals that come out here. One to do the address enable for the board, which basically says the CPU's got control of the bus and enable all these latches. And then when that goes to a high state, then in fact these latches and buffers are disabled, and then the DMA controller will be able to access the bus. And similarly then there's also a signal that comes out here that causes the clock and the microprocessor basically to pause. It doesn't actually use the built-in microprocessor hold and hold acknowledge. It actually just effectively pauses the microprocessor using the address enable on the clock controller. Now in order to get this working, I ended up having to add the X bus data bus. I was having problems early on, and to be honest, I've gone around in circles that many times on this. I really need to sort of restart all this from the beginning. But basically what we've got here is a dedicated address bus just for the DMA controller. Now the original PC design, we did cover this, and there was an area on the design that just had the interrupt controllers, the timers and things like that were all sharing this bit of bus. I think it was primarily because the bus couldn't handle the number of devices on it, but I did add this extra stuff here. So it added some complexity. So we got a bidirectional buffer to separate this bit of bus from everything else. In particular, I thought in the early stages that this latch could be getting confused by various things. And there's also a DMA IO PLD here where there were some reports that some of the DMA controllers didn't necessarily decode the IO read and IO write with the chip select, and so they could also randomly actually get corrupted if an address happens to address this, but the chip select and the IO read write weren't decoded properly inside. So I don't know if any of that's true. I've tried an awful lot of things to see if we can actually make this work reliably, but unfortunately I've not been successful so far. So what happens when the floppy disk controller has been sent the commands? So we've got our BIOS in ROM, it's been sent the commands to the floppy disk controller. The floppy disk drive has gone off to go and find the data, and when the first byte arrives, what happens is the floppy disk controller sends the DMA request signal on channel 2, to the DMA controller. Then what happens is the DMA controller will then request access to the bus. Once the confirmation of this has come through by pausing the CPU and disabling the buffers and latches here, then the DMA controller is then notified of this, and it is then able to send the DAC2 signal to the floppy disk controller. Now what DAC2 says to the floppy disk controller is, can you now provide me the data on the data bus please? So it doesn't require the chip selects and things like that to be active. The DAC2 actually says, put whatever data you've got in your data buffer here and put it onto the data bus. Now at the same time, what the DMA controller does is actually puts the lower 8 bits of address bus down here, and as part of the cycle what it actually does as well, it outputs the top 8 bits of the address, so A18 to A15 goes on the data bus here during a fairly short period of time where this address strobe signal. So effectively what happens is the DMA controller says put the top 8 bits here and then output the 8 bits there, so there's a valid address on here, and then what will also happen is the DMA controller will then provide the IO read and the memory write signals as well. And what that basically then does is then the data will then be provided by the floppy disk controller and it will go directly into the required memory. Now this repeats for all 512 bytes, and when it gets to the end here, the counter in the controller says, oh, I've got to the end, and it actually sends the end of process, which is inverted to become the terminal count, and that tells the floppy disk controller that in fact the last byte required by the DMA controller is completed and the whole cycle finishes. And the final bit of the process is the floppy disk controller signals an interrupt, and that interrupt is then actually picked up by the BIOS. So this is the whole process we covered in this previous diagram, and you can imagine that if any one thing goes wrong anywhere here, then it all goes wrong in a big way. So in fact, the areas where I've actually had problems are as follows. So the biggest problem that I've had is actually just the writing the values to the registers in here, and also the fact that sometimes the values that are appearing on the address bus there and on here get reversed. When that happens, it actually results in quite a problematic problem, that what happens, in fact, the DMA controller ends up writing over the lower area of RAM here, which is where all the interrupt vectors and things go. And so when then an interrupt occurs, then basically bad things happen. So this has probably been the biggest issue, and that's one of the reasons why I included this X bus here. The fact that the diagnostic ROM is unable to write and then read the same data from the DMA controller has also been problematic as well. There were some other issues to do with sometimes I was getting invalid data on the data bus. I think that was largely due to there being slightly too many chips on the data bus, and probably need a bit more buffering on some of the boards like the video card and things like that. I've also checked over a lot of the timing here. I've tried all sorts of different timing signals, and in fact the ones that I've got there work. Whenever I've changed them to be closer to what the official timing should be, then things have actually got worse. So to cut a long story short, I've done an awful lot of work here to try and get all this working reliably. I can boot DOS 2.10, but I haven't been able to reliably boot any of the later versions. So what I've also done then is I've looked at some of the tests that I did in some of the early videos. So I've now got a test 4, which is a RAM to RAM test. So basically what the DMA controller allows you to do is to use channel 0 and channel 1 to be able to copy one area of RAM to another area of RAM. So the reads use channel 0 and the writes use channel 1. Now you can't do this on the PCXT and original PC because channel 0 is used to refresh the dynamic RAM. It's not something that you can really add to the diagnostic ROM. It would basically break certain things. And what these tests are doing is it's testing the DMA register for 7 64K blocks. So we're starting at 0, going up to 6. Because the test code runs at 7000, we don't really want to run it there. And what happens is each block uses just 256 bytes starting at 1K area. The lower 1K is used by interrupt vectors. And we basically just put 0 to FF there. And it uses about 251 DMA requests for the remaining area there to copy those bytes to the remaining RAM. And then it goes through and tests the 256 byte blocks to see that they've got the sequential values in there and logs any exceptions to the power on self-test port. And what this is really trying to do is to do high volumes of copying data to check to see whether the addresses are getting reversed and whether or not, in particular, if the most significant byte and the least significant byte get reversed, then that may very well end up overwriting some of the lower memory. So I've started up the nanocomp and we're just going to send the file down. And then before we actually run the program, we're just going to make sure the two logic analyzers are actually looking at this. Okay, so I've got the two logic analyzers set up here. So on the right hand side here, we've got the power on self-test port output, which is triggered on the post clock. Then over here, we've got the 32 channel, where we've got the address lines, the data lines, the IO read and write, memory read and write, and then we've got the address strobe, which is the DMA. So this is the DMA activity that we can probably most easily see. So just going to start both of those, and then we're going to run the program. In fact, that's finished. Now what you can see here is where we're reading the register values, then I've got it to output a byte value here when there's actually a problem. So we've got the FA for address, FC for the counter, and I think FB is for the start address. So you can see here that there's actually quite a number of these problems. Now, what in fact the code does is if it detects that there's actually a problem with it, then it just goes through and repeats it. So what we can see here then is that we've actually got some blocks of these problems here. And if we go over onto the right hand side here, what we can see here, these are all the blocks where we're actually doing our DMA. So if we go into the first one here, we can see that in fact, rather than being one block, each one of these is the individual 256 byte block that we're doing. So you can see here that we're reading from 400 and we're actually writing to 500. We're doing that for all the bytes there. If we actually look at the last byte, we'll see that we're doing FF. So you can see there that we're copying 4FF to 5FF and the value is FF, which is being written. We can see down here the write is for FF. So this allows us to actually check to see that things are actually working as they would be otherwise be expected. What you can see though is where there's an irregular gap between some of these, this indicates where there's a problem with the, so you can see here that we've actually had to try multiple times to actually get the register values. So these are the reads from the registers and these are the writes. So here we've actually got, this is when it's working properly. You can see we've got just a handful of these there. In fact here you can see we've got 1, 2, 3, 4, 5, perhaps 6 retries to go here. So that's definitely indicates that something's not right. And we can see here that that's the first block. So this will be for the 0 DMA paid register. Then we'll have 1, 2, 3, 4, 5 and 6. So this indicates that things are working reasonably well, and in fact, because when we do the checks, if there's any problems with the memory, then in fact what we don't see is a lot of writes to the IO port here that would actually show where there were problems, because we'd be writing the block address here. So the fact that that is clear is good. And there is another version of the program which I did where I suppressed all of these messages here because these are all being handled. We're just retrying where this particular problem occurs. So it isn't in itself a problem. And just to make it a bit clearer, when there was a block which wasn't matching what was expected, given it's actually running cleanly, we don't really need to worry about it. So this indicates this indicates where the problem is occurring that the diagnostic ROM is picking up, and this indicates that the DMA process overall, once we've worked around that problem, then it is actually working okay. So in order to try and work out what was going on, I had another look through the data sheets, both the original Intel data sheet and also the Intercell one. And one of the things I did notice is that the ready signal, which is to do with wait states, so it's an input to extend the memory read and write pulses. Ready must not make transitions during its specified setup and hold time. And that, as another note actually in the Intel datasheet to treat the ready input as synchronous input. If a transition occurs during setup hold window, erratic operation may result. Now, I had further look, and I did actually look up on some Microsoft Copilot. So synchronization and metastability. So if we do have problems with asynchronous inputs rather than synchronous, then metastability occurs when a flip-flop is in an unstable state between logic levels. So the flip-flops control the DMA least significant byte and most significant byte on writes and reads. In this state, we cannot predict when a flip-flop will settle to a valid logic state. So it sounded like there could be something related to that. And it also further, this link also then says the setup hold window. So the setup time is the minimum time before the clock edge when the input data must be stable. Now, in fact, in the data sheet, it's about 60 nanoseconds out of a 210 nanosecond clock. So that's about 29% of the clock cycle. That's quite a long time. The hold time is only 20 nanoseconds or 10%. And again, it can lead to erratic behavior. So I was pretty sure that this sounded like it could be a problem. So if we have a look at the DMA ready signals in the data sheet, so the DMA ready signal going low will extend the read and write cycles for memory access. We can see here we've got 210 nanoseconds is the clock time for the DMA clock, and we can see here that the TRH and TRS, these are periods which need to satisfy these minimums. So you can see here that the ready to clock low setup time, 60 nanoseconds is the minimum time. Now, in fact, if you look at this diagram here, the gap here is actually very small. I suspect that is only about 20 nanoseconds. So in reality, this diagram's not very accurate and really probably should be showing that this gap here should be closer to this amount of time. So I thought, well, that looks like it could be a good explanation for why we're getting this erratic behavior, particularly where these flip-flops that control between the most significant, least significant byte, that might explain it. So this is overlaid with the DMA clock, the IO write and the ready signals, and we can actually see here that this yellow ready signal is actually overlapping with the DMA clock, and that really we need to move that DMA clock high to low transition probably 60 to 70 nanoseconds over that way. Now, to cut a long story short, I went through a lot of the different various clocks and clock cycles we've got, various inverted ones, corrected, changed various clock settings, but some of the settings would make the register read and writing work okay, but then the general DMA access didn't work. And then we tried a few others and shifted the DMA clock by 70 nanoseconds, should fix it. And basically all these things I did, and it didn't actually make any difference to the overall stability. And then I used inverted system clock, and basically I came to the conclusion that in the current design, probably I could spend another 3 to 6 months actually trying to get the DMA working. So I started to think about alternatives, and in fact, when I was doing some background reading on this, the PC Junior, so this was the IBM sort of consumer PC, and the Tandy 1000 didn't in fact use DMA. Since the PC Junior didn't have DMA, the BIOS routines for handling floppy access were different and more complex than those on the PC. Now, what I would say is, and more complex, I would argue the case for that, because I can't really see how anything could be more complex than the diagram that I showed you a little earlier about all the various things that all need to cooperate and work completely in step for a read of the floppy disk drive through DMA. And then the original Tandy 1000, the designers omitted DMA because the PC Junior didn't have one. And I suspect that this was actually probably a major simplification and reduced some of the components and the complexity quite a bit. And obviously the issue here is that we could actually just use programmed I/O. So that basically means that we use the processor to poll the floppy disk controller to see when there's data available. And the irony is that it's not as if the BIOS actually does anything useful. Basically, the BIOS just goes round in a loop, possibly using a timer, but otherwise just goes around in a loop waiting for the interrupt 6 to actually occur. So in actual fact, it's not as if when running DOS that the computer is able to go off and do useful activity, because basically when you do the BIOS call, it basically just spins round in a loop, or possibly uses a timer to spend a little less time sort of in a tight loop to wait for the interrupt to occur or to flag a timeout. So really it would indicate that we should actually be able to modify that and actually get it to be programmed floppy disk I/O. And when I was looking at the XT IDE universal BIOS, so this is the disk BIOS that we're going to look at using for adding an IDE hard disk, then in actual fact what this in fact supports is PIO transfer, so programmed I/O. Now the issue here is that on the original 8088 running at 4.77 megahertz, then DMA probably was faster than programmed I/O. However, the speed at which DMA could work at would be up to about 450 kilobytes per second. Now, the disks at that point in time, floppy disks, were probably a maximum of 360k, and it would take many seconds to read that amount of data off the floppy disk. So really, DMA was a bit of a sledgehammer to crack a nut at the time, and with the introduction of the 286 and the 386, then programmed I/O would actually be quite a bit faster, and in fact DMA had to continue to work at about 4.75 megahertz for backward compatibility, and so really was a lot of complication for not very much benefit. So I have come to the conclusion that what I'm going to do is to try and avoid using DMA going forwards, and if it was good enough for IBM and for Tandy, I'm going to have a look and see whether or not I can update the BIOS to have an option for doing programmed I/O for floppy disk access, and hopefully that will give me the ability to be able to boot later versions of MS-DOS after PC-DOS 2.10. So coming back to the high-level plan, I'm going to close out this phase of the floppy disk PC. I haven't quite been able to run MS-DOS 3.3 or MS-DOS 4, but I believe it is down to this DMA instability issues. Now in future projects I might have a look at doing this again and doing it a bit cleaner, and perhaps having another stab at this. But for the moment, what I'm going to be doing in the next video, what I'm going to start looking at is adding the real-time clock and the IDE disk controller, and in fact looking at the IDE BIOS as well. And in the background what I'll also be doing is looking at updating the BIOS to do PIO, programmed I/O, for the floppy disk access. So that basically just means that rather than having a loop waiting for the interrupt to occur, then we need to have a loop that reads the data off the disk and puts it in RAM, and then just waits until such time as it's done the last byte that we're expecting. So if you don't want to miss out on future videos, you want to see how to get an IDE disk controller working, then please subscribe to the channel, and if you could also hit like, it just helps to make the videos appear to a wide number of people. Thanks for watching.